Thank you very much. So I will give you a very technical talk. I'm from ThinkCell. We're doing software in Berlin. We're a pretty successful software company, and we're always, always looking for C++ developers. And today I want to present you a small, fun open source project that we have started out of a small business need that we had. Who here has experience with web programming in general? Okay, like everybody does that. And who of you has experience with WebAssembly? Like doing C++ to web stuff. Okay, cool. Node.js? Okay. So let me start by showing you what we built. So here in the comments, you have JavaScript code. That does nothing very interesting. It just adds some text on a website. And now there is this emscripten framework that lets you program a website in C++. And that would look like this. So that's not very pretty. It does the job, but you see it passes a lot of things as strings to JavaScript. So there's, from the C++ perspective, there's no type checking at all. There's no guarantee that this document exists or that this create element call is actually not a typo. So that sucks. Wouldn't it be better if we could write something like this, which would be a bit more C++-y, and then we do this, and then we set the text. So that's a JavaScript string now, of course. And then we set some formatting. Okay, set the font size to 20 so you can see something. And then last but not least, I add that to the website. Okay, this looks a bit more C++-y, and I can compile this. And now, of course, compilation always takes a bit longer than we would like. And what happens is, drum roll, oh, I get a compiler error. That's unfortunate. But what does the compiler error say? It says, hey, here, there's no matching member function for that call to font size. And it tells me, hey, there is a style sheet style decoration font size, but that takes a string and not a number. And now I say, yes, I remember web programming. This size is actually a string because you have to specify the unit. That's what you have a compiler for. I wouldn't have caught that bug without testing.
Ich habe diesen Titel nicht auf
Yeah, thanks. That's also an error. So that's one bug in my very complicated application that my compiler caught for me. Okay, so now it's built. Now we can go to that example. And lo and behold, it worked. So why did we build such a thing? Well, what happened? Let me first start by saying what happened. So what happens here is that we have a tool that can take type definition from Node, which are written in TypeScript, and then it calls a compiler on those TypeScript interface definitions and outputs C++ header files. So you can make type-safe calls from C++ to a JavaScript API. And why do we need that? Why can't we just program in JavaScript? So there's a tiny web application that we've built. Usually we have a desktop application. You can check us out on the website. We have a tiny web application that does one thing. It lets you import a chart from tableau.com. And then it opens this little web application where you can map the columns and the series and the values of your data to those of our stack charts. And then you can import it in PowerPoint. And this here, what you see is ThinkCell running in PowerPoint. And then you get that chart. You get that chart you had on the website before, and it remains linked. That's one of the features here. It remains linked to the data you had on the Tableau website. So when the tableau.com data changes, you can update that chart in PowerPoint. That web application has like 1,000 lines. It's not very complicated. And it has one interesting problem that it has to solve. There is data that comes in a tabular database format, and we have to transform that into a data table that we can put into a chart. So the individual data values can be numbers, strings, or dates. And now we want to sort them. We want to make them unique. And then we have to make a sequence of binary searches so we can put those values into the correct places of a data table. Now, that's a very simple algorithm. So we tried programming that in JavaScript. And that was surprisingly hard. So first, I wanted to sort an array. And that's what the documentation says. The default sort order is ascending, and it sorts strings by comparing, it compares everything by converting it to a string and then comparing the string value of every data. That's very surprising. And even worse, the time and space complexity of the sort cannot be guaranteed. Well, that's nothing you want in your real application. And to make matters worse, of course, there was no algorithm to get the unique elements out of a range, and there wasn't a binary search either. So I did what every good JavaScript developer does. I went to NPM, and I looked for binary search, and the first result isn't binary search. I think the second result was binary search, but at least at that time, it's a while ago I checked, it had some problems. At the very least, it would have overflown, I think, on very large arrays. So, I mean, this is something very simple. This is something you want to have in your language, and in that language, it should have defined behavior, and it should have defined complexity, and this should just work. And in C++, this would have been relatively easy, which is not something you say often about C++. So the data value would have been a variant of double, string, or a time point. Then I would have a vector of those things. I would sort it. I would get the unique range out of those elements, and then there is a defined binary search with the logarithmic runtime I would like. So this is what I would like to program my web application. First of all, I mean, we are a company that has a lot of C++ developers. This is what we're good at. And also, even in such a tiny web application, there is some code you want to share. There's some communication between the main application and the web application, maybe even algorithms we would like to share. So doing web development in C++ might be very convenient for us. When we can compile C++ for the web, then we want to call JavaScript because there might be existing APIs we want to call. And then we want those calls to be type safe. So doing web development with C++ is what WebAssembly has been developed for. And that's not a new technology. There have been a lot of talks at VIScon, for example, over the years. So this will be a very short introduction to WebAssembly. WebAssembly is a binary format that you can compile to from different languages, not only C++. And it has been standardized and is supported by all major browser vendors, which is very good. It's a fast and compact binary format, which has two low-level data types, integers and floating point numbers. And every WebAssembly module runs in a secure per application sandbox, even separated from the JavaScript virtual machine by default. WebAssembly modules are instantiated and can interact with, instantiated from JavaScript and can interact with the JavaScript environment. So let's say you have a WebAssembly binary with some function A that can declare some imports that it would get from JavaScript, and it can declare exports that are callable from JavaScript. And it can also export its memory object. So like your normal hardware, the WebAssembly module runs on a block of memory that knows nothing about garbage collection or anything. It's just a raw block of bytes. So in JavaScript, this would look like this. Maybe we declare some functions that our WebAssembly module wants to import for error handling. Then we instantiate the WebAssembly module with the binary blob we've downloaded from somewhere, and then we can call the exported functions. WebAssembly also has a standardized text format that looks a bit like disassembly, that is relatively easy to read, and even has some higher level constructs like if statements, for example. Now, in order to compile C++ to the web, you need the compiler, which is Clang in that case, and emscripten is an entire toolchain that wraps both the compiler and the runtime functions that you need so that your WebAssembly modules can do something useful. Most of the time, that would be maybe drawing OpenGL or creating sound output or interacting with the user through the keyboard and the mouse. So this has been emscripten has been very successful, and for example, has been very successful in porting games to the web, to the browser, because these are typically very self-contained, and all they need is OpenGL output and some mouse or keyboard interaction. Okay, so now we can compile C++ for the web. But how does calling JavaScript from C++ compile to WebAssembly look like? So I've mentioned one way those two can interact. They can import and export functions. But these functions, they are declared as C functions, for example, in C++. They're limited to the data types that WebAssembly supports. And I've said in passing, WebAssembly supports two data types, which are integer and floating point numbers. So when you want to call a WebAssembly function, you cannot pass a string to it, for example, just a number that somehow has to represent that string, for example. Emscripten also lets you embed JavaScript code in C++ directly, which is pretty funky, by using that macro. But those macros are also limited to those integer and floating point input and output values. So they're not super useful. And then there's this API that I showed you initially, emscripten val API, which lets you transliterate JavaScript code to C++ code. And then it looks, for example, like this. And it has the problems I mentioned initially, that there's essentially no type checking at all. So you pass all the JavaScript names by string. There's no guarantee that those methods exist. There's no guarantee that it has the return type I'm declaring here, or that anything will actually work. So that combines, well, starting with the advantages. It's good that this works. It's very convenient because it's easy to remember how this works. But it combines the disadvantages of both languages. So now you have something that, unlike JavaScript, you have to compile, and then this compilation doesn't give you anything. So that's not a very winning combination. Internally, this emscripten runtime works by declaring some functions in C++ that are implemented on the JavaScript side. And these let emscripten interact, or that emscripten implement that interaction from the JavaScript world to the C++ world. So we have functions that create a new JavaScript object and then return something, increase or decrease reference counts, or call a method on an emscripten object. And how are they roughly implemented? Well, this mValueObject method, for example, is implemented in JavaScript and is then called from the WebAssembly side. And it's actually just JavaScript code that would create a new JavaScript object with no properties, with nothing, would create a reference count to that object, and then store that object together with its reference count in some data structure, in a map in JavaScript, and would return an integer handle to that object, to C++, to WebAssembly. There's another method that lets you create a JavaScript string from a C string, so from a zero-terminated sequence of characters in your memory blob that works in a similar way. This would create an empty JavaScript string on the JavaScript side, and then read that C string from the memory block byte by byte and append each character to that JavaScript string. And then again, return a handle to the C++ world. And then you can imagine how the rest works. What you're passing back and forth between WebAssembly and JavaScript are just handles to objects and C strings. And the JavaScript side has to do all those lookups. What object is this? Return the object or call a function on that object, etc. So instead of this, we would like to write something that maybe looks like this. Maybe you can imagine something that looks even nicer, but this is something we can do at the moment. So you can have type check calls. You can be sure that those methods exist and that they return the objects you actually expect them to return. And this is what our tool Typescripten does. So it takes TypeScript interface declarations, and I will go into more detail what that is, for JavaScript libraries and compiles them to C++ interfaces so that you can make type-safe and somewhat idiomatic calls to JavaScript libraries from C++ via emscripten. So whereas in JavaScript you would maybe write something like that, assigning a string to a title, now in C++ we write something like this and do the same thing. And currently this project is still pretty experimental, and there's also experimental integration into emscripten in progress to get this more exposure, so to speak. But we've used it in practice. So what are TypeScript interface definitions? Well, they look like this. So this is the interface definition written in TypeScript for the JavaScript document element that you probably know from the standard JavaScript DOM API. And here you can see this document object has some base classes. It has a URL property that is read-only, that is a string. There's an active element in your document, which can be null. And there's a collection of anchors and a string title that is settable. Now, TypeScript ships with type definition libraries for the entire standard JavaScript library. And it has constructs to add type constraints to JavaScript in its entire complexity. So this thing, for example, I might have, if I have time, I can go into detail what that means. And not only does it ship with type interface definitions for the standard JavaScript library, but there's also this online repository where people can submit TypeScript definitions for arbitrary JavaScript libraries, which is pretty cool. And now we can take all of these, hopefully, and compile them to C++ headers, so we can interface with them from a WebAssembly application. And the cool thing in TypeScript is not only that it ships with those type definition libraries, but it also comes with a very powerful compiler API. So we didn't even have to do the work of parsing those things ourselves. We could use the TypeScript API, and this is a very simple code snippet that would take a file, parse it, and then iterate over all the source files, all the syntax nodes in that file, and then you can ask questions. Is that syntax node here in that declaration file, is that a function declaration or a variable statement? If it's a function declaration, what's its return type, its name, its arguments, its generic template parameters, etc. So that is very cool. Saved us a lot of time. And what our tool does is essentially it creates a header that looks a bit like this, that wraps the untype-safe emscripten API and generates a type-safe C++ wrapper around it, here for the document title property, for example. Okay, so who here has experience with TypeScript? Very, very nice. Well, we built the web app first, this little web app first in TypeScript, and it was nice enough, I would say. So now you have a compiler. You have a little project that tries to translate language constructs from one language to language constructs in an entirely different language. And that gets interesting pretty quickly because those two languages are very, very different. So this is, for example, valid TypeScript, where you have a function that has an argument, and this argument has not a specific type, it only has a constraint that this, the type of A has to have a length property. You don't care about anything else. Now, this is something that is hard to express in a statically typed language like C++. Not impossible with some template or concept magic, but it's not trivial. But luckily, we don't have to support all the TypeScript language features, at least not at first. First of all, because our input files are actually variable, we could write them in simpler ways if we wanted to. But luckily, we only have to support the typical cases that we find. And typically, for example, programmers are lazy, or maybe not so lazy, and would introduce a name for that thing just to make the interface definition file easier to read or to be able to reuse that thing somewhere else. So now suddenly that looks like a type that we can translate to C++. But that being said, we do support quite a lot of TypeScript constructs. So we have implementations for all the built-in types, any undefined null string, of course. We have optional members. We have type guards, which in TypeScript are a mixture of a type check and a cast. So you can check, does that object satisfy some contract, and then return it as a casted object. We support union types. We support mixed enumerations, which are TypeScript features, where unlike in C++, the enumeration can have integer, string, and floating point values. We even can pass C++ functions as callbacks to JavaScript, which I find pretty funky, to be honest. And we also support TypeScript generic types. And it is, for some time now already, it is self-hosting. That means it understood enough of the interface definition for the TypeScript compiler itself, so we could write it using itself, so to speak. So it is written in C++ and uses its own generated interface to the TypeScript compiler API. And yes, it also compiles all the standard libraries and the DOM library and Node and whatever. So this little TypeScript snippet I've shown you before, how that compiler API can be used, looks relatively similar in C++. And here in that highlighted line, you can see that I'm passing a C++ lambda to JavaScript as that callback to be called for each syntax node. Now, there are a couple of interesting semantical differences when you're doing that you encounter. So, first of all, in C++, there's this one definition rule. You can only declare a type at a single location. That's something TypeScript doesn't care about. It will merge all the declarations of all types it finds when they have the same name. The type system is different. We have static types in C++, and we have something different in TypeScript. And it goes down to the details, that sometimes you have different overloading rules, as I found out. So, for example, in this example, you have an array, and it has a constructor. It has two constructors. And one of them takes a number, which is the number of items. And then there's a second one, which if t is a number, would also be able to take one number. And now I'm pretty sure in C++ this would be ambiguous. But surprisingly, in TypeScript, it just does something. It takes the first one, to be honest. But I'm not sure if it always takes the first one or if there's a deeper language reason that it takes the simpler one. I haven't tried that. Maybe it just takes the first one. And of course, there are built-in types with very special semantics in TypeScript, like unions, intersections, or literal types, which can be a type of two string literals, or the union thereof, that we don't have in C++. And there were two priorities in that order in developing that tool. First of all, of course, I always want to generate valid C++ that compiles. And only in a second step do I want to make sure that I have a complete translation. So it's better to not translate something or leave it as in any object without any further types, as long as the result still compiles. Then there were some design decisions to make. So maybe you've noticed that. So when this is our JavaScript statement, how do we want this to look in C++? We could probably write something that would look like this. So we have some left-hand side C++ object with some overloaded assignment operator, and then in the background, it does all the magic it needs to do to send that string to JavaScript, etc. Well, that's not a very good idea, because it hides a lot of things from you. It hides that this is not a trivial operation, as you would expect. It also hides that, what else was it? Well, it was the expensive operation that is I think, remember, one of the expensive operations is that getting the title property of the document. That isn't a cheap operation either. And then assigning that string isn't cheap either. So it would maybe be better to do this. We have a setter for the title that leaves one expensive operation that I would like to make explicit, which is this conversion from a C++ to a JavaScript string. And now that only has one problem, and that subtle problem maybe is that we changed the name of something while we converted it. So we had a title property in JavaScript that we could write to, And now we introduced a new name, setTitle, in our C++ translation. And there's nothing that guarantees us that this JavaScript object didn't already have a setTitle method. So it's not a very good idea to change the names. So we end up with this, which maybe looks a bit strange, but it avoids naming collisions. Now, what are the language features that were hard to translate? So in TypeScript, the declaration order of objects doesn't matter. And in C++, unfortunately, it does. So when you try to translate something like that from TypeScript to C++, you have to take care that you order all the objects that you find when you're emitting them in some useful order. So base classes before derived classes. Maybe you have to introduce forward declarations of all types, etc. And then in TypeScript, there are things like union types, and there are also intersection types, which are also pretty interesting. So union types in TypeScript are nothing like C++ unions. They don't have a discriminating enumeration value. So if you have a union of A, B, or C, there's no way to tell is this either A or B or C. In a way, it's all of these combined. And the definition of A or B or C is the type that has exactly the set of properties that A, B, and C have in common. So it's essentially the intersection of their individual properties. And consequently, it is constructible from any value that has these shared members. So D has absolutely no relation to A, B, or C, but this is valid TypeScript. And what we see here is the definition of the TypeScript type system. In TypeScript, a type is just a set of properties. This is called structural typing. The name of the type is irrelevant, which is why we could initially have that example where you have a type that is only anonymous and defined by the length property. This is also structural typing. This is always what a TypeScript or JavaScript type is defined as. It's just a bag of properties. Now in C++, of course, that's different. In C++, the type names actually matter. We have what is called static typing. But we can build something in C++ that is valid C++ and semantically correct and still useful. So we can have a union type, for example, A, B, and C, that would convert to the common base classes of A, B, and C, because that's certainly a valid transformation. We can also build a type that is convertible to a wider union that would include D, because then that set can only get smaller. That's also valid. We can also construct it from anything that would be that A, B, or C would be constructible from. And in practice, again, this is not even as limiting as it sounds, because very often, again, people don't like to repeat themselves, but they would introduce types, for example, with common base classes when they share the same members, and they wouldn't add this member again and again and again to each class, relying on that structural typing. So in practice, this is very often what you find, and then those semantical differences disappear somewhat. There are also those mixed enumerations in TypeScript. So this is valid TypeScript, where we exploit another customization point in our tool. We just emit a standard C++ enumeration for our users, and then there's the customization point where all the data is marshaled from the WebAssembly world to the C++ world. And we customize that marshalling and then say, well, instead of my C++ enumeration value, I have this compile time lookup, and, or it's not compile time, but this lookup, and instead send a JavaScript string value to my JavaScript world. Yes, here. Okay, now I'm going to show you something else. Let's say we have this super complex website, which is very unorderly, and I want to sort these items by their size, but the button doesn't do anything. It doesn't work yet. And what I would like to do is something like that. I can look up the button, and I want to add an event listener to it and call my onClick method. And here I have an onClick method. But I can't do it like this. I cannot pass a C++ function pointer to JavaScript and expect this to work. So instead, what we can do is we can build ourselves a little helper object. I know what, I have this prepared, so I don't have to type that much. Okay, so I have a little contraption here that declares my callback. What does this callback do? Well, it's a mouse event handler. It will collect all the diff elements from the websites and get a collection, a JavaScript object, a collection of HTML objects back. Then it can use rangy C++ code to iterate over them, collect them in a C++ vector. Then it can sort them using our ThingsLRange library. It will sort them by their client height. So this is all very convenient to write in C++ when it's very expressive, when you have good algorithms, and when you have a strong library. And then it can just append them to the website again in sorted order. Okay, now this should compile out of the box. There's no compile mistake in here. Are there any questions so far you'd like to ask? Okay, so this just worked. And then you go, and it works. And we call a C++ callback from JavaScript. And the coolest thing is actually that this is a surprisingly good development environment, where in the latest Google Chrome builds, Google Chrome supports debug symbols in your C++ WebAssembly. So it automatically finds my code. I can set breakpoints here. When I call this again, it stops at my breakpoint, and I can step through that code if I find the right key. And I can even look at the variables. So this is something that is really working, so to speak, and really, really usable. Okay, so maybe as a last example, so how does that work? What do you have to do to pass function objects back and forth? And why is that, from the programmer's point of view, maybe sometimes even a good idea to do all these contraptions? So what you would have in JavaScript is maybe something like this. Maybe you have some dynamic website, you create an object that has a constructor and says, okay, yeah, if you create me, then I create my button and I add an event listener to this button, and then I do something when that button is clicked. Now, the problem of programming in JavaScript or writing complex applications in JavaScript is that all these things are reference counted. That button, some button, is never deterministically destroyed. That button isn't destroyed, but that click handler we are passing somewhere to JavaScript, this is also reference counted. Your function object is reference counted. It holds your object alive. It's pretty hard to understand the state your application can be in at any one state. And when you have encountered a web application in your browser that suddenly stops responding, and you have to reload the page and then it works again, I always wonder, like, how often is that actually the cause? That somebody messed up their application states and nothing works anymore, because it's hard to reason about this. And in C++, this would be deterministic and in a way simpler, where you could have a button with a constructor and then your function callback. And it will also have a destructor that would be called in some place that you know. And it could remove the UI element, and it would also implicitly destroy the callback. So and this is what our application objects do, our function callback objects. So what they do in the background is they create a JavaScript function object. And that function object has some C++ function it would call. And that JavaScript function object will call over to the JavaScript side. And it will pass two integers, because that's all it can do. It will pass two pointers to the JavaScript world. A pointer to a static function in the C++ world, and a pointer to, well, its own instance, a this pointer. And inside that JavaScript function, that JavaScript callback, we will just create a normal JavaScript function object, which will actually be called when the button is clicked. And when that JavaScript function object is called, it will call back into the C++ world and pass those integers back into C++ land. And then in C++, we know it's a function pointer, we cast it to the correct type, and then we call it, and that works. And we also give our function object a detached function that sets this function pointer to null, and this is what we call when our C++ object goes out of scope. So that reference counted thing in JavaScript can live for as long as it wants. It won't call anything, and it won't crash our application. So and then we call back into C++ and cast everything, and then finally we end up in the function we've actually written. And I've said we support generics. So here, generics in TypeScript are pretty much the same thing as templates in C++. They can have constraints in TypeScript. So you can say a type should extend an enumeration, which we can translate in C++ as a template argument that is actually an enumeration. Again, that's not quite the same thing. You have to keep in mind the differences in the type systems, but it's close enough to be useful. These constraints could be expressed in C++. It's maybe something like this. You have a template argument that should derive from some other class. Again, in TypeScript, this means it should have the same properties as Node. In C++, it means it has to actually derive from that class. And then last but not least, there's this funny JavaScript syntax that you're probably familiar with, where in JavaScript, when you add an event listener, you pass a string as the first argument, specifying which event you want to register for. And then you pass a different callback in the end. And the TypeScript developers had to think, I think, probably really hard and really long about how you make this a type-safe interface. And what they came up with is this, which is called indexed access types, where you have an event listener interface which has a generic argument k that says, hey, this k has to be a key of that type. And then, okay, suddenly you have a list of valid strings that you can pass. And then they introduce this thing here, which says, well, document event map of k is then the type of that property. And this is impressive and a nice language feature, and it wasn't trivial to convert this to C++. But I can. It is possible. It is possible, and it works. So I could think of several ways to do this. You could think, well, maybe I generate an enumeration, and then you pass that enumeration value, but then you have to look up the type of the event callback somehow. So it should probably be a template, so you can make a compile time lookup. But then this all didn't look very nice. And there are actually user-defined string literals in C++ that you can define so that this is valid C++. I could mark those strings somehow as being a special event listener string. So this translates to this in C++, where I have a key of function, which is compile time, which is const expr. So we evaluate this at compile time, and we return this map that document event map corresponds to. We return a map of the permitted strings and the event type callbacks they correspond to, thanks to this awesome Boost HANA compile time library. If you're not familiar with that, that is also a very impressive work. Okay, and this is the very pretty C++ function declaration that makes this all work, which is, of course, an abomination, I think you would say, but it works. Okay, I'll skip the last live coding. We've seen how this works. This entire project would be unnecessary if the WebAssembly standardization would be somewhat quicker. There is a plan to introduce so-called interface types to WebAssembly, which would allow you to call JavaScript more directly for WebAssembly, essentially giving WebAssembly access to more complex type declarations. But that is still in a very early phase, and even then, you still need some space to experiment with how this should feel from a C++ point of view. And one important limitation currently is that we're only wrapping this emscripten API. So whenever you make a call with that library, with this generated header, we are passing a lot of strings back and forth from C++ to JavaScript, which of course is relatively slow. But there are some ideas how to optimize this by generating functions, for example. Okay, so I'll skip to the last slide, which is the most important slide, of course. So we're also always looking for C++ developers. If you're curious, you can check out what we do. It is pretty fun to work at ThinkCell in Berlin, if I haven't mentioned that. Okay, so now I'm open to a question. Yeah?
Yeah, thank you. Brilliant talk. I was just wondering, were you ever tempted to use a template to solve any of those problems?
Not in this project. I've seen templates before, but not in this project.
It wasn't required. Just as a reminder, I think you explained it, but why exactly are you doing this with C++ and not just, I mean, the beauty about TypeScript is that it has types compared to JavaScript, right? So your problem was just that some trivial things like ordering doesn't have proper semantics.
No, there were several reasons. So we built this little web app in TypeScript to get some experience doing web applications. And there were those challenges that JavaScript has such a bad algorithm library. This was a big problem because suddenly you start writing them yourself. And for a lot of the time you have them already in C++, especially if you are doing this for a long time. You probably have a very big algorithm library that extends the standard library significantly and that you know how to use already. And even in such a small application, code sharing is a real problem. So there was code we would like to share because those two send data back and forth. And it would be really convenient to have the same definition of that data and not copy-paste it into TypeScript. So that alone would have been a good reason, I think.
Yeah, maybe I have a dumb question, but I don't really program a lot, so please forgive me. So my question is, how do you write this code? Is it like great support for several IDEs and stuff like that? Because for example, I heavily rely on JetBrains products because they write like half the code for me. And what you described as a beautiful code, something like that, quite at the beginning, to me this this looked already super complicated. So are you actually really writing this cryptic looking code all by yourself, or?
Yes. Yeah. So it's typically, I mean, this tool generates code for me. It generates the boring code. So wherever that is possible, we do that. But otherwise, if you're not familiar with C++, that probably looks cryptic. But even
it's just C++.
It's just C++. It's not particularly cryptic. It is.
Support for C++.
Yeah. Yes. So yeah, our code base is probably 1 million lines of C++ code or something. 1 million or something, maybe more by now, excluding external libraries we use. And yes, that is all written by hand, essentially. Yeah. Sure. It's not that my Office probably has 100 million. Yeah. If you do this for long enough, it just accumulates. Any other question?
So this 1 million lines of code, this is kind of the core of things.
This is the entire product. Yes. And so having only 1 million lines of code after 20 years is probably more of an achievement than a problem.
I would say so.
Yeah. Okay, well, if you don't have any questions, I'll be here for a couple more minutes. You can also come to me. I have a plane to catch, unfortunately.
Thank you, Sebastian.
Thank you. See you, VIScon.